Hi everybody. In the last video we replaced these 5 transistors along here on this channel. We left these ones all original, and so far that's the only modification we've made to this whole kit. And as we saw, even using good quality transistors, making sure that they were matched, the front end there was matched, all that made absolutely no change and no difference. Now, I understand that you're going to say that I could have done distortion analysis and all these other big fancy tests, but I can assure you it basically would have made very little to no difference. Maybe a very minor amount, but nothing worth even dealing with. So now let's try to make some changes that will make a difference in the amplifier. As I said before, it doesn't matter how good or bad the components are, within reason of course. If the circuit design isn't correct, none of that other stuff is really going to make a big difference. It's really important that your actual circuit design is executed in such a way that it will work properly. And you can do things in a circuit design, and I'm saying this in a generalized sense. You can do things with that circuit design to be able to make it function more consistently over different variations, because remember, transistors and all active components are kind of like moving targets, whether it be a transistor or a vacuum tube or whatever you're talking about. Anything like that will change with its environment. So different current, different voltage, different temperature, all these things will affect how it works within the circuit. A well-designed circuit will have that factored in so that when those changes happen, it won't affect the outcome of what you want that circuit to do, if that makes sense. Now you can cut corners and make compromises, and those, in that case, what you do is you say, well, this circuit isn't going to be perfect, but I can live with the outcome. If it's just a little bit off of what it should be, it's good enough. GE, as we say in X-ray. It's GE. Good enough. So anyway, let's see what changes we can make now that will make an appreciable change in the circuit. Now, the first thing I want to address, and that's what this video is going to be, is the problem that we have of DC offset. DC offset is when you look at your speaker terminals, in this case. DC offset in general means that there is a DC level that is not zero. That's what offset is. So your common point when the circuit is at rest, when there's no changes taking place within the circuit, that DC level that it's sitting at, if it's not zero, if it's above or below zero, we refer to that as offset. And of course, on your speaker, when there's no signal, in a perfect world, you want exactly 0 volts, AC and DC. You want 0 signal, 0 voltage on your speakers. If you put DC voltage on your speakers, it's going to do a couple of things. Number one, it's going to add heat to the speakers because you have current flowing through that very low impedance or low resistance, DC resistance voice coil. An 8 ohm voice coil on an 8 ohm speaker may have a DC resistance of far less than 8 ohms, sometimes half or even less, 3 to 4 ohms, depending on the voice coil. So really, just a little bit of voltage across that can cause current to flow and can add heat to the speaker, which is not good. The other thing that offset will do is it will unbalance by that amount your actual signal. So what will happen is it could cause your signal to clip at one end before it will clip at the other. You'll get asymmetrical clipping. So for those reasons, you really want to have as close to 0 volts there as possible. Now, this circuit is GE, good enough. It only has tens of millivolts of offset. That is not ideal, but it's not going to destroy the average speaker. So, Your tweeters and mid-ranges will have a capacitor, which will decouple the DC offset from them. And your woofer is usually a very large voice coil that can handle more heat. And the little amount of heat that tens of millivolts will impart on it isn't going to damage or hurt anything that much. That being said, it could be better. And also, you want the ability to null that out. Now, the way this circuit is designed, as you saw, even with matched transistors, we had an offset here. And that is because there's so many little variables in this whole circuit that only if this circuit was ideal, if every component was exact and perfect and calculated it perfectly where it should be, would it ever be perfect. And that just doesn't happen. There's tolerances. Resistors have tolerances. Transistors have tolerances. Everything has tolerances, and they're affected by their environment, the voltage, the current, the temperature, all those things. So what we want to do is we want to be able to counteract that offset. How do we do that? Well, we're going to do that by adding another offset that's equal and opposite. And we're going to do that right here. So essentially, if I have a DC level here that I don't want, that's going to cause offset down here, I want to be able to null that out. I can play with component values all day long, but really that's a bad way to handle it, because if something changes in here due to temperature or current or whatever, you're going to get that offset back. If we put an adjustment in there that lets us vary that offset a little bit, we can null it out. So we can wait for the amplifier to kind of get into an equilibrium temperature-wise and voltage and current and all that. And while it's warmed up, it's going to be fairly stable at that point. It's going to settle to where this circuit is going to be happy. We can use that adjustment to null that off. Now, you don't want to really apply that at our input stage, this Class A input stage, because that's going to affect the input of the signal as well. But what we can do is we can put an offset voltage on our feedback circuit. And we can make that an offset voltage that can go positive or negative. So if you have a negative voltage here, you can move it more positive to get it to 0. Or if you have a positive voltage here, you can move it more negative to get to 0. In order to do that, we need a secondary power supply that's very high impedance that can go either positive voltage or negative voltage without affecting how our feedback circuit works. So it sounds complicated, but with a few small passive components, we can actually do this. Okay, here's our schematic with just one addition to it, and that's our offset adjustment or our offset null control. And it consists of 2 diodes. More about why these are here in a minute. 2 resistors, well, 3 resistors, I'm sorry, and a potentiometer. So you have 3 resistors, a pot, and 2 diodes, and we can do this whole thing. Now, first of all, it takes very, very, very little amount of voltage here to change the offset of this circuit, and I'm talking millivolts. And our big power supplies here and here we measured them, they clocked in at 20 some volts each, 20 volts each, correct? Up to 24 volts, I think. So you have a 48 volt potential between here and here. So the first thing we want to do is we don't want high current flowing through this from the base to the emitter. We want to limit the current. So you have to have a high resistance in here to limit how much current is in this. You don't want to waste a lot of power over nothing. So I'm using a couple of 47K resistors, and if you look, that's in series through here, and in the middle of it I have a 5K pot. So we have approximately 100,000 ohms here. In addition to that, we have a 100K resistor going into the base. So again, we're always going to have a high impedance. It's going to limit the current, but allow us to adjust the voltage, if that makes sense. Now, what is the purpose of these diodes? If you notice, there's two diodes here, and the center point of them is going to ground. Well, the first thing is we want this adjustment to be stable. If you don't have a reference to ground here with our control, this output is kind of going to be free floating between these, and it will be unstable. It'll float around. You'll never be able to keep it steady. So these diodes do two things. Number one, they steer the voltage in one direction, because you have positive here and negative here. So the arrow always points to the minus on a diode. And what you can see is, remember, diodes have a forward voltage drop. And once you get through that voltage drop, it becomes current. And that voltage really doesn't vary much. It'll change tiny little amounts with current, but it's pretty stable and pretty consistent. So if I put two diodes in series, the maximum voltage drop across this 5K resistor is going to be about 1.5 volts, 1 to 1.5 volts. And when we reference this center point to common or to ground, that's going to make this be a positive voltage and this be a negative voltage with respect to the wiper of this potentiometer. So what's going to happen is, as I rotate this pot from one end to the other, when it's in the dead center, you'll have 0 volts. When I roll it this way, it'll become more positive until it gets to this maximum 700 millivolts here. And if I roll it this way, it'll go negative voltage till it gets to about negative 700 millivolts. So this is kind of like a regulated power supply that's plus and minus, and it's high impedance. So the best way to do this is, let's install this in the amplifier and test it. And what I'm going to do is I'm going to pick off a couple of places. Right here, R6 is connected to our DC rail on the other side of R24. So I want to get, so I can go right here where this resistor is connected. So that's a pad I can catch. And where are we here? R8 is right here. It goes to the negative. So if I go to one side of R8 and the one side of R6, or in our case, we're going to do R5 and R7, you can see they're right next to one another on the board. So this is a really convenient place to get. I don't want to drill holes. I don't want to hack. So what we're going to do is just lift one leg of each one of these resistors, put our wire in there, and then attach this resistor back in where it belongs. Now here's the little circuit that we built that we're going to use. I just took a piece of just cheap circuit board. I cut it with a Dremel, sanded it down a little bit, and it's just point-to-point wiring. You can see in there. And there's the little diodes. If you look at an angle here, you can see the diodes, one there and one there. Our 100K resistor, and then our two 47Ks, and then our 5K pot. And then these are our leads. This will go to the positive DC rail. This will go to the negative DC rail. This will go to ground or common. And this is our output that's going to go to the base of Q4, or in our case, the base of, what is it, Q3. All right. Q4 is the left channel, Q3 is the right channel. We're modifying the right channel. So let me get it wired in there and I'll show you what it looks like. And let's demonstrate this before I do that. We'll put it on a power supply. Okay, so our little module is connected to my power supply. Let's turn this where we can see it. Let me grab an adjuster. There's a tweaker here. And hopefully nothing will short out on us. There we go. And here's the power supply up here. And I can turn the voltage up. Let's turn it up to plus and minus 24 volts, let's say. How's that? 24 volts. And notice there is no current flowing that's measurable by the, because I can only measure a minimum of 10 milliamps. So it's way less than 10 milliamps. It's just a tiny, and if you do the math, there's probably only less than 1 milliamp of current flowing there. Okay. Now looking at the output, which is the white wire, right now the way this thing's set, it's outputting an offset of positive 1.1 millivolts. See that? And if we rotate this pot, what's going to happen, do you think? You can see if I go one direction, it gets more positive. I can go all over the place with it. And if I go the other direction and cross over, it'll go negative. And you can see now I have negative voltage. So that is a offset null adjustment. So we'll set that close to 0 right now. And now we're going to wire that in to that circuit. And what we're going to do, as I said, we're going to put that white lead is going to eventually find its way right here on the base of Q4. The red lead is going to go here. The orange lead is going to go here. And then common ground is going to go to our common area, which is here, or here, wherever. I'll be right back after that's wired in. Okay, there is our little modification board, and tried not to make it look too janky in there. So we're picking up the ground, or the common point, off of R3. And I'll show you that here. So that would be right here. There's R3. We're picking up the positive and negative rails off of R5 right here, as I showed you earlier, and R7, because they're conveniently on the board right next to one another. And then right next to that is R4, or I'm sorry, R11 right here, where we put our white lead, or the output. So essentially we now have what you see right here. Okay, let's turn the meter on, and of course we always get weird millivoltage on here from the meter, and that's just the way this meter works when there's no current. Okay, let's turn the amp on. And you can see we have, because this was zeroed out, remember when we've zeroed it out, we have about 60 millivolts, just like it always was. So let's see now if we can rotate this pot, if that will lower that. And really the best way to do this is with nothing on the speaker terminals, and you should technically jumper out the input to get rid of the influence of any noise that might be coming in. But it's going to be minimal, and we're not going to worry about that. Okay, let's turn this. Going the wrong way. Okay, here we go. Look at that. And once you get to a certain point, you can adjust it. And look at that. Under 1 millivolt of offset. That's beautiful. Now, of course, after this amplifier is used a little bit and warms up and things get to equilibrium, this may drift the tiniest little amount, and we will make a second adjustment on it. And once we do that, that'll keep it pretty much in check. You can see it's actually changing a little bit now because the amplifier's been on for a while. And if we give it 10 or 15 minutes, we may be able to just touch it up a little bit more, but we'll see. But anyway, that's how this works, and it's as simple as that, to add DC offset to the amplifier. Now, I'm not going to test it in this particular video because we're going to do a couple more things, and then we'll do one final test after all of our mods are done. But that's how to deal with offset. Okay, both channels have the dummy load on them, and I have the oscilloscope and the THD meter attached to our modified circuit. let's see what we get. First, we'll look at the scope. And that's still a really good signal. And if we go to both channels, I don't have the other scope probe hooked up. Hold on. And you can see they look pretty much identical still. So you can't really see anything on the waveform. But let's go over to our distortion meter and see what happened. How about that? Let's move over to the other channel and see what it looks like. Wait a second. Still not bad. About the same. Little bit better on the other channel. So that's our modified channel with the offset adjustment. This is our unmodified without the offset. Not a whole lot different, is it? Okay, so we did add offset adjustment, but I think we can conclude that other than taking that little bit of DC off of your speaker during idle, it really didn't make any difference in the performance of the amplifier. So once again, it's nice to have for this particular instance, but really it's not going to make a huge difference in how the amp performs. We're going to have to do even more to this amp to see that happen. And that's going to be for the next video. So until then, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back real soon. Thank you. Bye-bye.